Good morning, everybody. Welcome to our machine learning seminar. Today, we'll have a pleasure to have a presentation from Dr. Jesús Fuentes from the Luxembourg Center for Systems Biomedicine of the University of Luxembourg. Today, the seminar for the first time will be formally part of the course of the doctoral school in science and engineering. So we'll have a number of PhD students who are attending the seminar. I asked them to switch on their cameras, so probably you can recognize them easily thanks to that. Anyways, I think it is a good initiative which will help the students to, it will create the possibility to see how machine learning is applied in research and industry in different contexts and in different disciplines as well. So it creates this platform to transfer skills between disciplines, between teams. So I hope it will they will find it useful. So not to make it too long, Jesús, the virtual floor is yours. The title is already present on the screen, so I will not read it. Please and go ahead.
Okay, good morning, everyone, and thank you so much, Jacob, for having me. My name is Jesús Fuentes. I am a postdoc at the LCSB. The topic that I am going to present today is rooted in quantum theory, but what I want to share with you today is a data-driven approach to reconstruct not only the state of quantum systems, but also the dynamical elements involved during the time evolution. And for these purposes, I am using neural networks. So this work is also not yet published, but currently
it doesn't bother you. It doesn't work right.
Sorry.
We can hear some echo, so I think somebody has his microphone not muted. Okay, thank you.
Okay, let me know when I can proceed.
Okay, Jesús, please go ahead.
Okay. Also, well, I was saying that given that this is a machine learning seminar, I will try to put more emphasis on the motivation behind as well as the use of neural networks instead of focusing on the physical theory involved. So I will try to avoid the jargon and all these fancy words that physicists used to employ. But in any case, please feel free at any moment to ask questions. Well, to begin with, this work is about orbits. And I want to start with this slide because I think it's intuitive for to all of us, but eventually I will move to a different case. So an orbit, broadly speaking, is the trajectory that a body describes when it moves around another body or while it is subject to the presence of a field. For instance, in our solar system, Earth describes a path around the sun because of the gravitational field exerted between them. So this path is closed, but there are cases in which orbits can be open. And there are also cases in which gravity plays no role, but instead it is the presence of other fields which promote the motion. Now, here is nowadays, we can compute with excellent accuracy the orbit of the Earth that the Earth describes around the Sun. And the same applies for other planets, of course, because of we know Kepler's laws, Newton's laws, etc. But assume for a moment and for an instant that we don't know these laws. So instead, we have an incomplete theory with some equations, but there's a missing part. So fortunately, let's assume that we have data, and maybe what we can do is to use our equations combined with that data to complete what we need. In this case, let's suppose that we don't know exactly the Earth's orbit around the Sun or any other planet, But the only thing we know is a portion of data and a set of incomplete equations. And we want to make predictions with what we have at hand, asking about the possibility of reconstructing the trajectory in its whole. So this question has an affirmative answer. And as I will show, using neural network combined with some equations, it is possible to reconstruct the paths that charged particles describe when they are subject to electromagnetic fields, for instance. During this talk, I will review both the classical and the quantum cases. So to be more precise, I don't know what it, okay. To be more precise, this is a summary of what I will show you. So I will use a differential, a universal class of differential equations of this form, where the time derivative on the left hand equals to some function of these dynamical variables, and these functions can be either linear or not, combined with some other derivatives. These derivatives can be over the coordinates or with respect to the momenta. And this other function here, phi, is the parameterization of the neural network. So, for instance, if phi is a neural network with two hidden layers, we can write it in this form, like here, where the W's are the weights of the network, the B's are the biases, and the sigmas are the activation functions. And also for simplicity, in what follows, I will omit any other derivative with respect to other variables involved during the evolution process. So this will be only focused the work today and the talk today on the time derivative of these dynamical variables. So let me start with the classical motion. As I told you during the introduction, the possibility of generate orbits for a particle is not only reduced to the interaction with other body, but also because of the presence of a field. In this case, consider a magnetic field which is aligned along the z-axis, and let us also consider a charged particle which is very, very massive. To put it into the context of a classical particle, of course. And let's assume that the speed that this particle describes is much less than the speed of light. So I'm basically dealing in the context of non-relativistic mechanics. So the motion that this particle will describe is well studied. In what classical electrodynamics tells us is that we have, after some algebra and some the application of some basic concepts in electrodynamics, we are led to these Hamilton's equations of motion. And they describe the helicoidal path of this particle around the principal axis of the magnetic field. This orbit can be either closed or open. It will depend on the kind of forces, external forces applied, and also on the kind of potential interaction of this particle. But that's what we already know from electrodynamics. Let's assume for a moment that we don't know these equations, or at least we just know some portion of these equations. But instead we have data, and we want to combine that amount of data with the incomplete equations or with the incomplete set of equations that we have at hand. So, for instance, let's assume that sorry for switching between slides, but let's assume that we know, for instance, this set of two partial, ordinary differential equations, but we do not know these other portions here, and we also do not know these forces indicated in this row vector here. So that's what I want to parameterize with the neural network, and that's each one of these unknown variables will be hidden or will be partially furnished by these elements of this neural network. Okay, so this is a completely arbitrary choice. You can even decide that the rest of the equations are also known and put other parameterizations here. This is just for a simple example. And what the theory tells me is that by integrating these equations of motion, the trajectory that this particle subject to a magnetic field aligned along the z-axis will describe orbit similar to this figure here. But again, let's assume that we know only a portion of this orbit, and that's what I'm going to do here. Just truncate the complete evolution of the trajectory of the particle to generate some data, and I will add also some noise to this data. And the objective is to use this parameterization combine it with some other elements that I will show you in the next slides, and see if in the first place, this trajectory can be reconstructed. This portion of truncated trajectory, I mean, can be reconstructed. And if the long-term prediction can also be reconstructed from this training data. So, to this aim, I'm using some modules in Julia, just to put some of these ideas in a kind of a complementary way to see this example more clear. I will put this code. And the code is not necessarily complete here, but it's just the idea. First, I defined a general neural network with the aim of these modules. It can be defined in another way using the modules of your preference. And then I define the system of equations that I want to parameterize. In this case, this corresponds to this parameterization here. And what I'm going to do is to treat this problem as an ODE, and I am going to use all these approach as a minimization, or in fact as an optimization problem. So what I'm doing here is just to put all these elements here and define them as an ODE problem, which will be optimized or which will be treated as an optimization problem, and then applying some optimizers, going or trying to approach to the optimal solution, or at least to the best possible solution. Okay, so today's aim, I'm using two optimizers, an Adam first, an Adam optimizer, and then BFGS. The reason is that the convergence is faster and even smoother than using only one of these optimizers. Also, to avoid some overtraining, I'm using an early stop block, but the problem in itself is a bit challenging because there can be a stiffness in the equation, and there will be a trade-off between the stiffness and the amount of data that can be used to feed the neural networks. And obviously, this will compromise the fitting of that of the model in itself. This fitting can even be underfit or even an overfitting. So I will talk more about this in a few slides. And well, after some experiments, some training and trial and error experiments with these models, I could reconstruct the partial trajectory of the dynamics involved in the first case, and I forgot to mention that I am feeding the model with 4 inputs, each one for each of the dynamical variables involved. So I will feed the model with the let me go back some slides. I will feed the model with the coordinates, with the 2 coordinates, x, y, and the respective momenta, one along the x-axis and the other along the y-axis. So although this is the momenta are not plotted here, it shall be understood that there's also a map similar to this, but for the case of the momenta. Sorry for omitting that part. And well, the thing is that, as I told you, after some numerical experiments, I could reconstruct this partial orbit of the that is described by the particle. And looking at the errors, well, it looks like a reasonable model, a reasonable numerical approximation. But let's see if it makes sense for real applications, for instance, in the quantum case. So also using that, once the network has been trained with this data, the next step is to see if the complete trajectory of the orbit can be or not reconstructed. And using the fitted parameters with the training data, I could reconstruct with a good approximation the orbit of this particle moving around a magnetic homogeneous field. There are some caveats here because for instance, the classical case can be modestly approximated and modestly reconstructed. But the orders of magnitude of the error could be also reasonable because of the level of applications that this kind of motion could have. But the problem that it's that for the quantum mechanical case, it can be not much the the optimal solution that we are looking for. So the message here is that, and I'm doing some, I am telling you some of the conclusions already, but what I want is to kind of discuss with you that even if the dynamical reconstruction is possible or at reasonably possible in the classical case, the quantum case deserves more attention and more care with regard to the numerical methods employed. So let me pass to the quantum motion, and but the motivation is exactly the same. It is about the reconstruction of orbits, and it is about the combination of data-driven approach with an incomplete set of dynamical equations to see if we can or not reconstruct what the particle or what the system is describing, or in the way that the system is behaving. So let me pass to this experimental setup, which is the very basic idea of an ion trap. Imagine that there is a cylinder made out of some conductive material, and there will be a magnetic field. It can be time dependent or not, but there will be an homogeneous magnetic field aligned along the z-axis, and also the cylinder will be fed with some electric scalar potential, for instance, in this case. But that's just the rough of the idea. So this is basically what we did for the classical case, but here I am adding some other physical elements in the picture. So now I started with some slide talking about the Earth's orbit around the sun. Then I introduced also this the motivation of this work with some classical orbits. But the question is now, what about quantum orbits? And that's why the title of this talk is fuzzy orbits. The reason is as follows. What we classically know as the trajectory of a particle in quantum mechanics is not necessarily the same. It's not like a path that we can draw with a pencil around some object and in paper, but it is something else. So don't worry because of the equations here. The only thing or the message of this slide is that in this case we must be careful with the treatment of orbits, because these are trajectories that exist, but we cannot see it directly or in the classical way that we are used to. The reason is that the coordinates of these trajectories, of the quantum trajectories, are not scalar quantities or vectorial quantities. These are operators, and it takes a challenge to imagine how exactly are those orbits being formed. But there are some quantum systems, for instance, the quadratic Hamiltonians, like this one here, in which the trajectories of a quantum body is or has some semi-classical approximation. And because of that, we are entitled to use some similar approach than as the one that I used some slides before. And it is more intuitive to imagine this kind of orbit just by appealing to this specific and particular kind of dynamical systems. So the kind of problem that I'm dealing with right now, which is the motion of a particle, of a charged particle around a magnetic field, has a quadratic Hamiltonian, and therefore it has a semi-classical approximation, because in fact the equations that are lying behind are very similar in theory structure to the Hamilton's equations of motion that I described for the charged particle in the classical case. So in a sense, and to summarize with this slide, what we understood by quantum orbits is nothing but the expected value of these operators here. And it's not necessarily, as I told you, a path that you can draw with a pencil, but imagine like a belt of uncertainty in which the particle can lie with a certain probability. So that's the idea of quantum orbits. So for this case, I will also use a time-dependent magnetic field, and I will proceed almost in the same way as before, but there will be some changes, of course. The first one is that, as I told you, here I am not going to reconstruct necessarily the ordinary differential equations of the Hamilton's equations of motion, but the operators involved during that evolution, or during that process of evolution over time. And to do that, I am also going to employ neural networks, but not for reconstructing necessarily the trajectory, but to reconstruct the operator involved in the generation of that trajectory. So, having said that, the problem can be simplified in many different ways, using some symmetries and making use of some other tricks. And the motion here can be decomposed in basically in three types of motion or operators involved during the motion. One is the first one, the most simple, is that given that the particle is interacting with a magnetic field which is aligned along the z-axis, so this motion is constant during the whole evolution and can be omitted. The second one is just the rotation of this this particle suffers during the time evolution, and it's can be integrated also in a very simple way. But the oscillatory part needs more attention and cannot be integrated directly as the other two components of the motion involved. So that's the part in which I will concentrate now to try to integrate this equation, but not analytically. In fact, it is not possible analytically, but not even following a standard numerical method, but a data-driven approach as before. So the aim here is basically to parameterize this equation here, this evolution equation here. So I'm going to use, again, a neural network to parameterize the matrix element of this operator, of this matrix here, or this operator here, the BT, which is the generator of the oscillatory motion. And you may be asking, okay, how are you collecting data in this case? How is the data being collected? Because in the classical case, even if it is the Earth's orbit or other planets' orbit around the sun or whatever, or also charger particle moving along the symmetry axis of a magnetic field, the velocities and the coordinates can be known simultaneously. But in the quantum case, it is not possible to know the position or the momentum simultaneously. There's an uncertainty between these two datum. So that's why I'm going to use another assumption, and I will appeal to a phenomenon which is called evolution loop. So the evolution loop is basically, in quantum mechanics, broadly speaking, is when the system returns to its very seminal conditions or to its initial conditions after a period of evolution. So the system will not only recover its initial coordinates, but also its initial momentum or velocities after some period of time. And because of that, the system will be evolving in kind of loops over time. So imagine that at a certain point, I will be collecting some data about the coordinates. And when the system returns to its initial conditions, then I will collect the information about the velocities or the momenta of the system. So this is a tricky way of collecting data, but theoretically it is possible, but I don't know if experimentally it is achievable. So there is a big gap between the paper and the laboratory, but let's assume that this can be done. At least it can be done numerically. So also for simplicity, magnetic field will depend on two quantities, on two different magnitudes. And this biharmonic case generates this stability map that you see here to the right. The white areas correspond to this motion that is stable over time, and the bluish areas correspond to unstable motion. But there's also a third kind of motion that can be classified here and correspond to these colored lines that you see here. This is known as parametric resonance. I'm not going to explain or to go at the level of detail on this, but I will just focus on the motion that is furnished by taking the magnitudes of this magnetic field that correspond to the stable areas. We'll try to see if the neural network or the model can not only reconstruct the operator involved, but also the magnitudes here that correspond to the clear areas or to the stable areas classified accordingly according to this map. So again, I'm going to generate an arbitrary loop with some initial conditions and with some parameters, and will truncate this case just to generate data. I will add some noise to make it more interesting, and also to try to circumvent some overfitting. And then I will use this trained data as the input of the model, and see if I can reconstruct what I was saying. Also, basically the procedure is very similar. The pipeline is to train the data, to train the model, to optimize. In this case, I use an Adam and BFGS optimizers, and see how is how are the errors behaving during the integration or during the training. And here is a thing that I want to discuss with you, because the problem that I'm trying to integrate, which is this one, this one, is it possesses a high stiffness. Stiffness is nothing but the sensitivity to the model to be to be unstable under upon the integration of certain numerical methods. So, for instance, some numerical methods cannot be used for certain problems or certain evolutive problems because of the size of the grid. So if one reduces arbitrarily the step of integration, one could think that the method will deliver better results than with a curved range, for instance. But in many cases, that's not necessarily the truth. Also, the opposite. If one chooses a step of integration kind of course with respect to other choices, the stability of the method can also be compromised. So this is a trade-off with the amount of data that I can choose to feed the model, because it is not necessarily the more data that will give me good fitting if, on the other hand, the stiffness or the stability of the method is compromised. So I don't exactly know how to optimally solve this problem. This is an open question. And the best that I can do until the moment is just a trial and error method to see if some kind of a step size in the integration can be reasonable or can induce reasonable results during the training of the model, and also to try to overfit. And this is a very important problem here, because the aim is that the model can learn to generalize data. and to detect exactly the patterns that are involved during the dynamical evolution, and see if this unseen data can or not be reconstructed. So I will leave this as an open question, and let me proceed in the way that I did before. So again, the model is fed with some noisy data. After some training, it is possible to reconstruct that portion of the trajectory. And then the long-term prediction also achieves reasonable results. But here, the orders of magnitude in the error are really important, because it induces an additional uncertainty to the system. As I told you, the path that quantum particle describe is not necessarily a classical one, but a belt where there lies some uncertainty. So if the error during this prediction is considerably or larger than the analytical or semi-analytical method that I am employing, so this would lead to add more uncertainty to the original belt of uncertainties that I have. So this can be part of the criticism that this work could receive. And let me go to the conclusions, and let me begin with the classical motion. Well, the classical equations of motion for a charged particle moving in an homogeneous magnetic induction field could be parameterized with a feed-forward neural network, and then the unknown parameters or the parameters that I hid to try to reconstruct this problem, it could be predicted by this network. And once the network was trained, the long-term prediction could also be approximated to a good degree of approximation, I mean. With respect to the quantum motion, I pursued a similar approach. The quantum dynamical case was, in this case, treated at the level of the evolution operators involved. To try to reconstruct these evolution operators, I also use a neural network to fit the parameters but the parameters associated with the oscillatory motion in this case. And the long-term prediction apparently achieved reasonable results, but yet for real applications, we still need to resolve the generalization problem, which remains as an open question. And that's what I wanted to show you and what I want to share with you. And thank you very much for your attention.
Jesus. Thank you, Jesus. Let's go to the question part. So I think there is a question from Sarah. Let me see, because I cannot read it. What kind of neural network you have used for the quantum notion? Was it also the feed-forward network? And what was the input? Exactly. What was the output? What was the loss function? I think this is the question, that because I also had a version of this question.
Yeah, exactly. Yeah. I used
it was not clear.
In fact, a very similar. I'm sorry, because this code cannot be quite quite good for representation.
I'm not used to Julia.
Okay. Yeah, but the idea is that it's very similar to the feed-forward neural network that I use for either for the quantum case or for the quantum dynamics scope. The input variables are the coordinates of in the classical case are the coordinates or the dynamical variables, which are the coordinates and the velocities or the momenta of that particle. And the output of this network is, in fact, the information that I want to obtain in the equation, the part that it is missing. And but in the quantum case, it's a little bit tricky because it's not necessarily the same. The output, again, are the canonical variables, the coordinates of position, and the velocities of that particle. But the output of that network is not necessarily, or does not have necessarily a physical meaning. It's just portion of this matrix of evolution that it is depicted here.
And what is the loss function?
That's a good question. Let me see if loss function. I don't exactly remember what was the loss function in each case, but I think that for those one interested in the project, I could share the code of this talk with, and hopefully you could run this code.
I see. And why did you use the Julia?
That's a good question. The reason is that I found some interesting examples in the same direction, but using Julia. And some other colleagues are also using these modules, but for other purposes. So I don't know. I just decided to try Julia and do something with Julia, but there's not necessarily a concrete or a strong argument to say that I'm using Julia because of that.
I see. And if anyone has a question, just switch on your mic and try asking. You can see Hamed has his microphone on, but Hamid, no. Okay.
May I ask my question?
Yes, Shara, please.
And you can hear me clearly?
Yep.
Okay. So sorry, my physics, I mean my study of physics stopped at the first 2 years of college, but couldn't we use more complicated neural network, like deeper networks? Because as I noticed, it was like you used just one hidden layer, right?
Oh no, it is. In fact, let me show you.
No, I mean
here. Yeah, here. It is not one. It is not only one hidden layer. It can be more hidden layers.
Why just feed forward? Why not using, I don't know, like LSTM, for example? Because it seems like a time series. Like, can't we feed it like with time series?
No, I haven't used an LSTM for this project in particular. I use LSTM network for other purposes, but yes, I think that the exercise can be done. Yeah, it could be also applied.
Thank you.
Thank you.
So it is not, may I ask a question as well, because in slide 7 maybe, but in general, that you, as far as I understood, you had some PDEs and some operator that is not known with those PDEs that you would like to fit with using your data and some assumed form of the operator, which in your case was the neural network model. And you used some gradient-based minimization to fit the data and to identify the parameters. And so is it a way to see the form of that operator, the real life, I mean, the mathematical form, analytical form of the operator, to see whether your neural network is at all capable to represent this nonlinearity that is present there, or I mean, to somehow to tell a priori by analyzing the formula that is given by your neural network operator and your analytical formula, whether in your case it's the neural network is capable of fitting the complexity of your operator or not, or maybe it will be tending to overfit it. Have you tried to
that's a very thank you very much for the question and for the feedback, because that's something that I haven't tried yet, but I think that this is one of the steps that I shall follow to try to overcome the overfitting, or to the trade-off between the stiffness and the overfitting in the quantum case in particular. But yeah, I haven't. The answer is that I haven't tried this yet. I think that it is very interesting.
I see, and for the quantum case, I'm the same as probably a large part of the audience. We are not that specialists in that particular field to have proper intuition what sort of problems you had to deal with to model it.
Yeah, thank you. But regardless of it is a classical or a quantum case, the message of the presentation today is to construct hybrid approaches that include data and that include some incomplete set of equations. I mean, maybe we just know something, or we have modeled something, or we have the idea, a very rough idea of some phenomenon. And these models, of course, can be incomplete because they are missing many parts. But on the other hand, we can complement these models with the data that we observe directly from the phenomenon, and use this approach or a similar approach to resolve this set of equations and try to feed the parameters and see if the model is giving us or not what we expect, or what we should expect from empirical experience or from data, or if it resolves or not the problem that we are trying to address. I think that that's the very objective or the goal of this talk. In the quantum case, I'm not reconstructing the equations of motion, but the operators, which are in this case matrices, that are related to the generation of the orbits involved during the evolution process. But again, the idea is, let's assume that we do not know that in matrices, but instead we know some data, and instead we assume that we have the ideal conditions that I mentioned, to collect that data and to fit that models, to see if that that thing that we can that we would like to recover is possible or not. Yeah, that I think that summarizes the objective of the talk today.
Right. Thank you, Jesus.
Thank you very much.
We are very close to 11, so probably we would have a time for a single question, but probably I don't see at least an raised hand. So thank you so much, Jesus, for presenting your topic and for giving us some more details in the discussion. And thanks to the audience for your attention and for taking part in the discussion. So I will keep you updated about the future seminars, and next one we'll have it next week, and I will keep you posted about this. So have a good day today, and see you next week. Bye bye.
Thank you very much. Bye bye.